This video is about emission spectra. The first key concept that we'll mention in this video is that an emission spectrum is formed when a gas emits electromagnetic radiation. So in order to explore how an emission spectrum is formed, we'll begin with a gas cloud. The first step is to supply energy to the gas cloud. That, for example, can be done by passing an electric current through the cloud. We learned in the previous video that when energy is supplied to the atoms in a gas, electrons in these atoms transition from lower to higher energy levels, or in other words, the electrons become excited. Also, as a result of this energy transfer, the temperature of the gas increases. Then, when we stop supplying energy to the gas begins to cool down, and now electrons in the gas atoms transition from higher to lower energy levels. Of course, during these transitions, electrons must emit energy. This energy is in the form of electromagnetic radiation, composed of photons. Now, for the purpose of our example here, we'll assume that this radiation falls into the visible light section of the electromagnetic spectrum. In the final step of this experiment, the radiation that is emitted by the gas cloud is passed through a prism that separates the radiation into different wavelengths, so as a result, an emission spectrum is formed. In a moment, we'll see how this spectrum looks like when the light emerging from the prism is projected onto a dark background, but first we'll discuss in terms of energy level transitions what exactly happens as the gas is cooling down. Now, this is a simplified energy level diagram, as it does not include energy values for the different levels. I decided not to include these values because they are not relevant to the concept that we want to explore here. So as we saw, in the beginning of our experiment, when energy is supplied to the gas, electrons in the gas atoms transition from lower to higher energy levels. For 4 energy levels, there are 6 possible transitions. Let's represent all 6 of these transitions using arrows of 6 different colors. As we mentioned, these transitions happen because the electrons absorb energy. Let's now see what happens as the gas starts to cool down. During this part of the process, electrons emit energy in the form of photons. Of course, this means that electrons move from higher to lower energy levels, so transitions now happen in the opposite direction. Let's draw these transitions on our second diagram. Now, as a result of these transitions, photons are emitted from the gas cloud. As there are 6 different transitions, the radiation emitted by the gas cloud contains photons of 6 different frequencies. Therefore, when this radiation is passed through a prism and projected onto a screen, we get 6 lines with 6 different colors on the screen. What we see here is called an emission spectrum. The red arrow on the diagram represents the lowest energy, hence lowest frequency transition, while the purple arrow represents the highest energy, so highest frequency transition. Therefore, on our emission spectrum, energy and frequency increase from left to right. Of course, this means that wavelength increases from right to left. Now, when we pass white light through a prism and project it on a screen, we get the entire continuous visible light section of the electromagnetic spectrum. Let's take a moment to discuss why in our example here we only get specific lines instead of the entire continuous spectrum. As we said, during each transition that is represented on the diagram, a photon is emitted by an electron. The longer an arrow, the more energy is emitted during a transition, which of course also means more energy carried by the emitted photon. The key here is that, as we learned in the previous video, energy levels are quantized, which means that the photons that are emitted by the gas cloud can have only 6 different energy values. These 6 different energy values correspond to 6 different frequencies, hence 6 different colors. This is the reason why we get 6 distinct lines on the screen instead of getting the entire continuous spectrum. Logically, photons that carry more energy will produce lines closer to the violet end of the spectrum. So as you can see, the longest arrow corresponds to the violet line, and the shortest one corresponds to the red line. Let's finish up by adding a key practical use of emission spectra. It is that since each chemical element has a different emission spectrum, emission spectra can be used to identify elements. This technique is used, for example, to identify the composition of stars. Since each chemical element has a unique emission spectrum, similar to how each person has a unique fingerprint, when light from a star is passed through a prism and projected onto a screen, the emission spectrum that we get can be compared with the emission spectrum of known elements. Doing so helps us deduce the chemical composition of the given star. With this final point, we have completed our learning about emission spectra.